In the real world, data is massive. A single image has millions of pixels. A financial model has thousands of market indicators. We call this the curse of dimensionality. When you have 10,000 features, your data becomes sparse. Your distance calculations break down, and your models get incredibly slow. And visualization is impossible. We can't draw a 10,000 dimensional graph. So, how do we fix this? How do we take this massive high dimensional monster and squash it down to just 2 or 3 dimensions without losing the important information? The answer is principal component analysis, and the secret to unlocking it is the eigenvectors. Welcome to Decoding Complexities. I'm Pradeep. Before we write the code, we need to understand what PCA is. It is a deterministic 5-step linear algebra algorithm. Let's break down exactly what each step achieves. First step is centering, meaning we shift the entire dataset so that the average point sits exactly at the origin. This ensures that our math measures the spread of the data, not its location. And the second step is standardization. We scale the features so they are comparable. If one feature is measured in millimeters and another is kilometers, the math gets biased. Standardization puts all features on a level playing field. And the third step is the covariance matrix. We calculate a square matrix that summarizes how different features move together. This acts as a map of the data shape and direction. And the fourth step is eigen decomposition. We find the eigenvalues and the eigenvectors of that covariance map. These vectors represent the principal components, the new hidden axis where the information is most concentrated. And the last step is projection. We multiply our original data by these eigenvectors. This effectively rotates the dataset, aligning the useful signal with the axis and pushing the noise to the side. Let's look at the mathematical engine of this process. The most critical step is calculating the covariance matrix. If our data matrix X is centered, the covariance matrix is simply X transpose times X divided by the number of samples. This matrix sigma is a summary of the entire dataset. The diagonal tells us the variance of each feature, how spread out the data is. And the off diagonals tells us the correlation, how features move together. Our goal is to find the vector v that maximizes the variance. Mathematically, this means solving the eigenvalue equation for this covariance matrix. If we solve this, the eigenvectors become our new axis, and the eigenvalues tell us how much information they hold. This is the blueprint. Now let's build it in Python. To make this intuitive, we'll create a dataset of 200 people with 2 features, height and weight. We generate the data so they are correlated. Let's look at the raw data we are generating. Height is around 170 and weight is around 70. The scales are different. If we run PCA now, height will dominate the math just because the numbers are bigger. So we execute step 1 and 2. We subtract the mean and divide by the standard deviation. Now, a tall person and the heavy person are measured in the same units. Now, we apply the formula we just saw, the covariance matrix. This matrix captures the shape of our data cloud. And the step 4 is to calculate the eigenvalues and eigenvectors. We sort them in the descending order. The largest eigenvalue corresponds to the most important axis PC1. Before we proceed, let's visualize what the math found. Look at the red arrow. This is PC1. It points exactly along the diagonal spread. The math found the relationship between height and weight automatically. This axis represents size. Now, for the projection, we rotate the data. And here is the result. The data is flat. The x-axis is now PC1 with maximum variance. And the y-axis is PC2, which is mostly noise. Notice the red arrow is much longer, visually proving it holds more information. How do we know how much is that information? We check the explained variance ratio. PC1 captures 86% of the variance. This means we can throw away the second dimension and still retain 86% of the signal. In a 10-dimensional dataset, it allows us to compress massive data into a few simple axes. But in the real world, data matrices are rectangular. You cannot calculate eigenvectors of a rectangular matrix directly. So, how do we decompose any matrix of any shape? This leads us to the fundamental theorem of linear algebra, the singular value decomposition. This is the topic of our next video. Link for the companion blog post and the collab notebook is in the description. Hit that like button and subscribe to continue decoding the complexities of machine learning. Thank you for watching, and I will see you in the next one.